Okay, gentlemen, turn off your mobiles. Keep your mobiles in the pockets throughout the class. For the attendance, look at the complete name on screen. Salam alaikum. Ahmed Abbas. Bender Sultan. Abdullah Muhammad. Muhammad Mustafa. Muhammad Ahmad. Hussain Jafar. Saud Fahad. Abdullah Suleiman. Saud Abdul Aziz. Salman Fahad. Muhammad Ahmad. Salman Abdullah. Faisal Fahad. Muhammad Abdullah. Fahad Khalid. Abdurrahman Adil. Muhammad Suleiman. Muhammad Ahmad. Hamid Hani. Muhammad Haytham. Pradeep Farooq. Ibrahim Hussain. Where is he? Yusuf Muhammad. Hussain Abdul. Hassan Ahmad. Abdul Hadi. Ahmad. Jawad. Ahmad Mirza. Abdul Aziz. Ahmad Assam. Mishal. Saad Ahmad. Fahad Saeed. Abdul Aziz, Abdurrahman. Those who came during the attendance. Number 5, Muhammad Ahmad. 9, Saud Abdul Aziz. 11, Muhammad Ahmad. 16, Abdurrahman Adil. Anyone else? Okay, let us review what we have done so far in these 5 classes. Yes. Okay, in those 5 classes, what we have done is we have derived the estimated model for this simple linear regression model. This is called simple linear regression model. And to estimate this simple linear regression model, we made a number of assumptions. And based on those assumptions, we have an estimated version of this model. The estimated version of this model is yi hat. This is beta naught hat plus beta 1 hat times xi. Now the formulas that we derived for beta naught hat and beta 1 hat, these formulas are derived through a method called least square estimation. And these estimates are SXY over SXX. Some of you called it SXY, some of you called it in business statistics as SXY. So it's the same thing with the different notations. Now there are several formulas for this SXY and SXX. But all of them are mathematically equivalent. For example, the easiest formula for SXY, it is a summation of xi yi minus summation of xi times summation of yi over n. This is the easiest working formula for SXY. There is another form of SXY which is available in literature. This is summation of xi minus x bar times yi minus y bar. If you open the bracket and apply the summation, you will get to know this is the same as the one before. Another form of SXY is summation of xi minus x bar times yi. Again, if you open if you multiply and then apply the summation, you will see it's the same as the first 2 forms. So all these forms are equivalent. There is mathematically no difference between 3 of them. Similarly, there are formulas for SXX where the easiest formula is summation xi square minus summation xi whole square over n. And I repeatedly, I'm saying that these 2 things are different because I know many of you will still make this mistake. These 2 things are different. Another form for SXX is summation of xi minus x bar whole square. And these 2 forms, again, they are equivalent forms. There is no difference between the 2 of them.
Are you sure about the last rule in the SXY?
SXY? Yes.
Because it doesn't make sense that
It doesn't make sense?
a number multiplied by a number is equal to a number multiplied by a number minus 1.
It's it is. It is. Because the second number is 0. It's what? The second one, if you multiply it with the first one, it will be this term. If you multiply it with y bar, what it will be? It will be xi y bar minus x bar y bar, right? When you apply summation, both of them will be nx bar y bar, nx bar y bar minus nx bar y bar will be 0. The second term will be 0. Anyhow, if you want to practice how to open the square and apply the summation, there are just a couple of steps, like keep the summation outside and open the bracket inside. There is xi minus 2 times xi x bar plus x bar square. That's how you open the square, a minus b whole square, right? Xi square. Then you apply the summation. The first term is a complete variable. You will apply the summation as it is. The second term, it has a variable part, it has a constant part. What is the constant part? This is the constant, sorry. Two and x bar is the constant part. The constant part goes out of the summation, 2x bar, and summation is applied only on. The third thing is completely a constant. So you add a constant n times, what is the result? N times that constant. Summation x. Can I write this summation x to be nx bar? Because x bar is nothing but summation x over n, which means summation x can be written as nx bar, and there is nx bar square. There is nx bar square minus 2 times nx bar square. This thing minus 2 times the same thing. What's the result? Minus nx bar square. And now you open nx bar square and you will get the result. It is summation x over n whole square, right? So there are two n's in the denominator, one n in the numerator. One of them will cancel out. And you will have summation xi whole square over n. So these two forms are mathematically equal, exactly equal. Again. Now, apart from all this discussion, we did use the easiest possible formulas in Excel to estimate these beta naught hat and beta 1 to get the values of beta naught hat and beta 1 hat. And finally, when you have it, you plug it into the model, and this is your estimated model. This is the estimated model. Using the estimated model, you can have the predicted values of y. Now, once the estimation is done, what do we do next? Once the estimation of beta naught and beta 1 is done through beta naught hat and beta 1 hat respectively, what is the next stage in statistics? There is descriptive statistics, then there's probability theory, then there is sampling distribution, then there is point estimation, then there is interval estimation, and hypothesis testing, of course. So now is the time to evaluate how good your regression line is. Inference, confidence intervals. To do that, you will notice later that this term will help you, the errors will help you, the residuals will help you, which are the actual values minus the predicted values. How will they help you? I will answer that after 2 classes. When I'm done with the derivations of the variances of beta naught hat and beta 1 hat. So at this point, At this point, when I'm done getting the formulas of beta naught hat and beta 1 hat, I'm going to talk about the distributions of beta naught hat and beta 1 hat. Exactly on the similar pattern, let me discuss. A single variable case. You have this population on X. Single variable case. Go back to the previous course, 211, 201, 319, a single variable case. This is the population of X. This population is modeled by a function, f of X. Okay. You take a sample from this population, and that sample is of size n. The model of this population has some unknown parameters inside the functional form, like it can be the mean, it can be the variance, the median, the mode, the quartiles, and many more unknown parameters. They are hidden inside the function. Many characteristics of the population are unknown. All of them are unknown, basically. Now, let us say this is the parameter of interest. This is all previous course. Let's say this mu is the parameter of interest, which is the population mean. What do you do with the sample? You calculate X bar, which is summation Xi over n. And you say that this X bar, is a point estimate of this mu. True? Once you are done with the point estimation, you give a statement that the point estimates are never equal to the parameters. Sometimes they can be close, sometimes they are far, but they are never equal to mu. As long as X is constant, the probability that X bar is equal to mu is 0. It will never be equal to mu. They can only be close to the parameter. They will never be equal to the parameter. Now, ideally, what do we want? We want them to be close to the parameter. Yes. How do we know whether they are going to be close or they are going to be far? To answer this question, I introduce another concept, which is the sampling distribution. What is that concept? The concept says, let's say I pick a sample of size n from one population and I calculate X bar. And let us say X bar comes out to be 17.2. This is a fixed population. Okay. I call it X bar 1. This is my first sample. Now, my question is, if I take another sample from the same population, another random sample from the same population, and I calculate X bar from that sample, will it be 17.2? Will it change? The answer is it can change. It can change, right? It can change. Let us say it is 18.1. Let's say it changed. Okay. Then I pick another sample, X bar 3. I calculate the sample mean of the third sample. Can it change? Can you tell me whether it will be 17.2, less than 17.2, 18.1, or more than 18.1, or in between these two? Do you have any idea? Can you predict? So we get to know two things about X bar. Number one, from sample to sample, it's changing. It can change. Something that changes is called what? Variable. And secondly, we notice it is changing unpredictably. If I tell you a sequence of 10 values of X bar, you cannot predict 11th. It is changing unpredictably. Something that is changing unpredictably is called what? Random. All in all, X bar is a random variable. It's a random variable. True. Now, our probability theory says that every random variable has a distribution. The probability theory says every random variable has a distribution. Sometimes it's a well-known distribution, sometimes it's not a well-known distribution. Well-known distributions are normal, binomial, Poisson, exponential, gamma. There are many well-known distributions. Sometimes you are unable to recognize the functional form of this f of x. It's not matching with any well-known function. But for every random variable, there is a probability distribution. And in this case, I should say the sampling distribution, because X bar is a statistic, an estimator. So the probability distribution of an estimator, we use the term sampling distribution for the probability distribution in this case. The probability distribution of original variables, we call it probability distribution. And the probability distribution of these estimators, we give a different name to them. We call them sampling distributions. The things are same. Just the background concept is different. That one is for the actual variable from the nature, and the other one is the distribution of a statistic, not the actual variable. Now, your probability theory says that if x is normal, what will be the distribution of x bar? Why will it be normal? Because x bar is nothing but a linear combination of x. What is x bar? It is 1 over n times x1 plus x2 plus x3 plus all the way up to xn. So x bar is nothing, but it's just the summation of normal random variables. X1 is normal, x2 is normal, x3 is normal, all the way up to xn is normal. All of them, they have the same distribution f of x because they are coming from the same population. So according to the theory, these normal random variables, if you add two normal random variables, the result is again normal. Right? What happened? Which means if x follow a normal distribution, then x bar will also follow a normal distribution. We did study this with the same mean, but a different variance, a smaller variance. By the way, why smaller variance? Because x bar is more compact than x. You can expect less variation in the x bar. Let's say if I pick one student from this class and try to predict the score of that one student, the student can score anywhere from 0 to 100. There is more variation in one student. What if I pick 10 students and talk about the average score of 10 students? Now there will be less variation. So of course, x bar, it is more compact than x. You can expect less variation. Yes.
Smaller, we expect higher variation.
If the data is less, you expect higher variation. If the data is more, you expect less variation. In X bar, you have more data. You have, let's say, n values. Assuming n is more than 1. If it is 1, they are both same. X and X bar are same.
So there is no chance for X bar to be, so to the variance to be higher than X.
The variance to be higher than, no. Cannot be. Now, based on this last distribution, you define a z statistic. What is that? X bar minus its mean divided by its standard error. You remember that? Based on this z distribution, you defined a confidence interval that was x bar plus minus z alpha by 2 times sigma over square root of n. You remember that? And then you criticized this thing by saying that usually in the practical life, this thing is not known. You criticize it. You are saying that the objective of this whole story is to estimate an unknown parameter mu. When mu is unknown, then why you are assuming that another side parameter sigma is known? You said it is hardly available in real life. So what do? You replace this sigma by its estimator, true? You replace this sigma by its estimator S. And what happens when you replace sigma by S? The resulting distribution becomes T. It's no longer Z. And the resulting confidence interval is this. So this statistic can be used for testing any hypothesis regarding mu, and this is the confidence interval for mu. Yes. Let's forget about that thing. Let's not go into the approximations. No matter how large n is, the exact distribution of this thing will always be T. It's another fact that when n is bigger, it gets closer to the Z. But let's not go into the approximation. Let's talk exact. Exactly, this thing is always T. Because what we are going to do in this course is we have Excel available. So you don't need to use the tables. Even if I give you 4000 n, you can find a critical value directly from T. No problem with the critical values. We don't need to go into the approximations. Excel can give you the critical values of Z and T for anything.
So you want tables?
No. You won't be using tables. In this course, you will not be using any tables. Excel will give you the critical values, exact critical values. The reason you go for the approximation is you see the T table. In the T table, the first column is n-1. So there are limited values of n-1. You cannot make a T table for n-1, 1, 2, 3, 4, all the way up to 7,000. You can make a limited table. So if the degree of freedom for your question is out of that table, you don't have anything. Let's say 100, 120, whatever. You can even make it to 1,000, still limited. You cannot make it from 1 to infinity. We don't have that limitation here. In Excel, you have everything available. So we'll not go into that third case. We'll not actually go into all of this. I'm going to connect all of this to a bivariate case now. This whole story, I'm going to connect it with a bivariate case. And before I connect it, I repeat it. I have an unknown population on single variable. This unknown population is modeled by a probability density function f of x. This density function depends upon some unknown constants. These are called the parameters of distribution. One of those parameters is unknown. And you are interested, all of them, basically all of them are unknown. You are interested in one of them. Let's say you are interested in that mu. To estimate that mu, you take a sample. From the sample, you calculate the point estimate. Then theoretically, you discuss that this point estimate is unpredictably changing, so you call it a random variable. Then you start talking about the probability distribution of this random variable, and you say that this probability distribution is named as sampling distribution just to differentiate between x and x bar. You discuss that if x is normal, x bar, the distribution of x bar is exactly normal. And then you define a Z statistic for testing hypothesis about mu. And you define a confidence interval for the interval estimate of that mu. Similarly, you criticize the Z statistic and the confidence interval based on it, because that interval is using a very strong assumption. And that assumption is that sigma is known, which is not really true in practical life. So the solution is that you replace that sigma by its estimator. And when you replace that, the resulting distribution of the statistic changes from Z to T. And also the confidence interval changes from Z to T. Now, let us go back to the same scenario where we have a bivariate population. We have X1, Y1 as the first pair. We have X2, Y2 as the second pair. We have X3, Y3 as the third pair, and many more pairs. Infinite many pairs are there in the population. In this population, we are assuming that X and Y has a relationship, and that relationship is the unknown parameter. We are assuming that X and Y, they have this relationship. This is the line, the unknown regression line. And I'm not putting hat. This is the actual unknown regression line, and this line is the unknown parameter, like mu. This time, it's a line and not a constant mu. To estimate this unknown parameter, what do? You take a sample of size n. That means you pick n pairs from this population, and from those n pairs, what do? You calculate beta 1 hat and you calculate beta naught hat. True? Using the formulas that we derived. You calculate them. And you say these are, and you write down this yi hat equals beta naught hat plus beta 1 hat times xi, and you say this is the point estimate of these parameters respectively. Beta naught hat is the point estimate of beta naught, beta 1 hat is the point estimate of beta 1. The thing doesn't stop there. You don't stop at the point estimation. What do? You go further for interval estimation, and to do the interval estimation, we repeat the same story. If I take another sample from the same population, will the slope and intercept change? Can change unpredictably, which means that these two quantities, beta naught hat and beta 1 hat, are random variables. If they're random variables, they will have a distribution. True? So now the discussion is about the distribution. I'll start with the distribution of slope first, because this is easier. Then on the same pattern, I'll move on to the distribution of intercept. To derive the distribution of this beta 1 hat, I'm going to define a supporting variable here. And that supporting variable is Ci. And this is just a function of x. It is xi minus x bar over Sxx. Why am I doing that? When I do that, you will see this C will be appearing everywhere in the distribution of beta 1 hat. But before I do that, I'll find some of the properties of this C. The first property I'm going to find for this C is I'm going to find this summation of Ci. What will be the summation of this Ci? Sxx is a constant. When I apply the summation, what will happen? 1 over Sxx, I will have summation of xi minus x bar. True? What is the sum of deviations taken from mean? Sum of deviations taken from mean? 0. Or you can mathematically prove it. 1 over Sxx, apply the summation, you have summation xi minus nx bar. True? Summation x is nx bar. So it's nx bar minus nx bar, which is. So we proved that summation of Ci is 0. I will use this thing later. Then What is summation of Ci square? True? Sorry, when I say Ci square, this will also be square, whole square. True? What is this? What is summation xi minus x bar whole square? It is sxx. So this thing in the rectangle, it is sxx. So it is 1 over sxx square times sxx, which is simply 1 over sxx. Summation Ci square came out to be 1 over sxx. And last one is summation Ci xi. These three will be used. So I multiply summation Ci is xi minus x bar over sxx times xi. Right? Sxx again is a constant, it will go out. And I will have summation of xi square minus xi x bar. True? I multiplied xi inside. Now apply the summation. What do I get? I will have summation of xi square minus x bar times summation of xi. True? What is x bar? Summation x over n. X bar is summation x over n. And there is another summation x, so it becomes square. True? What is this? Again, sxx. So it is sxx over sxx, which is 1. So I found three properties of this variable Ci. I found summation of Ci is 0, summation of Ci square is 1 over sxx, and summation of Ci xi is 1. Why am I doing that? I'm doing that because this beta 1 hat, which is the sxy over sxx, is nothing but summation Ciyi. It's nothing but summation Ciyi. How? Let me put Ci. What is Ci? Correct? I take sxx outside and I have summation of xi minus x bar times yi. What is this? Where is it? The one in the circle. The third form of sxy. This is sxy. So what do I get? I get this one to be sxy over sxx, which is beta 1 hat, is it? Why am I interested in proving that beta 1 hat is summation Ciyi? The answer is I'm trying to prove that some beta 1 hat is nothing but a linear combination of y, because I know the distribution of y. What is the distribution of y? What was the distribution of y? Go back one step further. What was the distribution of epsilon? What is the distribution of epsilon? Normal, What is this whole thing? Constant. So a normal random variable, if you add something to the normal distribution, what happens? Say stays normal. Sorry, there is no hat here. Yi is normal. If yi is normal, that means this is normal, right? What is ci? Ci is all function of x, and x is constant. True? So it's beta 1 hat is nothing but a constant multiplied by yi plus a constant multiplied by y2 plus a constant multiplied by y3 plus a constant multiplied by y4 and so on. If you open this beta 1 hat, which is summation of ci yi, if you open this, this is c1 y1 plus c2 y2 plus all the way up to cn yn, right? Where c's are constants. So beta 1 hat is nothing but a linear combination of y, which means if you are assuming that epsilon are normal, y's are normal, beta 1 hat is normal. So we get the first result, which is the distribution, the sampling distribution, like X bar is normal, right? We get the similar result that beta 1 hat is normal.
Both of them, the sample and the population are normal.
Beta 1 is a constant value like mu. There is no distribution for a constant value. Compare beta 1 by mu and compare beta 1 hat by X bar. So like you say, you are estimating mu, here you are estimating beta 1. And the point estimate is beta 1 hat. And you're trying to derive the sampling distribution of this point estimate to get to the confidence intervals and hypothesis testing stage. Now, what you do for X bar, you said X bar follows normal distribution with something and something. The first question mark is what? What is the mean of X bar? It's the same mu. And the second thing is sigma square over n. We are going to fill these question marks for beta 1 hat in the next class, inshallah. Once you fill these question marks, what will happen? The distribution of beta 1 hat will be complete. True? Then you will define a z statistic, which will be beta 1 hat minus its mean divided by its standard deviation. Then you will criticize this z statistic. You will say that there is an unknown quantity in that statistic. That unknown quantity will be what? Sigma or sigma square. Then you will replace this sigma square by its estimator. And the resulting distribution will change from z to t. Whole story, same story, no difference. Then based on that t, you will define the confidence interval for beta 1. You will define the testing hypothesis for beta 1. Any question from today's class? I deliberately stop here. I have 5 minutes. In 5 minutes, I can derive both these question marks. But this will be too much in one class. Yes. In X bar, it's not a relationship. I'm telling you the pattern we follow in statistics. The pattern we follow in statistics is that there is a problem, there is an unknown parameter. The way we tackle it is that we try to estimate that unknown thing from the sample. Once we estimate it, then we try to see its unreliability. It's how much is its variation. The same pattern or process we follow. Why are we using CI? The answer lies when I try to find the mean of beta 1 hat and the variance of beta 1 hat. To fill those question marks, you will see CI will come. The properties, yeah, the properties of CI will come there. It will be very, very helpful. Just 2 steps and you'll be able to find the mean. 2 steps and you'll be. Why am I writing beta 1 hat in this form? Just to show that beta 1 hat is nothing but a linear combination of y multiplied by some constants. I deliberately defined Ci such that there is only x in the Ci. There is no y in the Ci. There is no epsilon in the Ci, which means we are assuming x is to be fixed, which means whole Ci is fixed. Yes.
Yeah, any value of you just define it to use it in the other steps.
It's practically I'll not be using it anywhere. When I do solve the questions on Excel, I'll never be using CIs. This is all mathematical to find the properties of beta naught hat and beta 1 hat. That's the only objective of defining CI. Any other questions? I am expecting one question. Nobody has asked that yet. Will this come in exam?
Yes, no. No. I think we are learning this just to do the questions and exercise. So we don't need to know that. To get our target on.
Go back and see some past exams of 310. Go back and see some past exams of 310.
You are agreeing with him?
I'm agreeing with him.
So we're waiting for him to see the.
Yes, go back and see some past exams of 310.
No, like. Will try and see it.
Let's hope not.
You don't know.
No questions? Any questions regarding the lecture? No questions? Also, I'll try to,